Okay, here we're going to start talking about number patterns and sigma notation. And sigma notation is also sometimes known as summation notation. You'll probably hear me call it that. And the number patterns specifically that we're going to talk about have to do with things known as arithmetic sequences and geometric sequences. And then we're also going to talk about series. And series has to do with, well, adding a bunch of stuff up. Well, let's start off here, though, with something different. So let's start off with sequences. So a sequence is simply a list of numbers in a defined order. So they come in a specific order. So I've got the sequence 1, 2, 3, 4, 5. Well, that's just a finite sequence because we have, well, finitely many terms. So that's a sequence. Again, it comes in a very specific order. So, the sequence 5, 4, 3, 2, 1, that would be a different sequence because you're getting the numbers in a different order. So the next sequence, we've got -5, -7, -5, -3, -1, etc. And that goes on forever and ever and ever. That's what the 3 dots mean. So that's going to be an infinite sequence because it keeps going. And I think you can probably spot the pattern to that one. Notice it does have a nice clear pattern. And then the next sequence, we've got 16, 8, 4, 2, 1, 1/2, etc. Again, another infinite sequence because it's going on forever and ever. So for a lot of sequences, it's possible to find a rule or a mathematical formula. So we're trying to find a mathematical rule or a formula to describe the sequence. So I think the first one's probably pretty easy. Let's look at, let me label this as A and this is B. Let's see if we can come up with a formula for the terms here. And these are actually going to have special names, so that's why we're going to talk about them a little bit. So we've got -7, -5, -3, -1, 1, etc. Well, to go from one term to the next, what are we doing? Well, it looks like to me we're adding 2 each time, so that's the pattern to this sequence. Well, generically, we can label our terms. So -7, that's going to correspond to my first term. And we'll use different letters. I'm going to use U's. I used to always use A's in my mathematical career, so if you see me using A's at first, that's just going to be a force of habit. But we'll try to use U's in general. So U sub 1 would correspond to -7. Then I've got U sub 2, U sub 3. And in general, I'm going to have some generic nth term. And again, it keeps going. Well, let's see if we can spot a pattern here. So U sub 1, well, that's just -7. U sub 2, I'm adding 2. And notice I could write the number -5 because that's what U sub 2 equals, but I'm trying to spot the pattern. So what am I doing to get U sub 3? Well, I'm adding 4, or equivalently, I'm adding 2 multiples of 2. U sub 4, I'm adding 3 multiples of 2. So in general, to get the nth term, it looks like I'm starting at -7, and I'm adding 1 fewer multiples of 2. So I would have 2 multiplied by the quantity n minus 1. And that would be a formula for my nth term for this sequence. And this sequence where we're adding numbers, the same number each time, this is what's known as an arithmetic sequence. Now notice this formula too. We could distribute out the +2. We would get -7 plus 2n minus 2. We could simplify that and rewrite it. So we could simplify this formula a little bit and rewrite it. So that's one thing to recognize. There's not a unique formula for the general term. I mean, they'll all be equivalent, but you may see it written in a different form is what I'm trying to say. So always expand out a few terms if you have, maybe if you're checking your work. Expand out a few terms and see if you're getting the correct values. Okay, so we said we're adding the same number each time, +2, +2, +2. That number is often labeled as D, which is called the common difference. So that's the number that you're adding, or you could be subtracting as well. You don't have to add a number, you could be subtracting a number as well. So that's part A. Let's look at a formula for the next one too. So we've got this sequence 16, 8, 4, 2, 1, 1/2, etc. So 16 is going to be my first term, u sub 1. My second term will be u sub 2, that'll be 8. U sub 3 will be 4. U sub 5 will be 2. And we can go on and on. So what am I doing? Well, my first term I start at 16. To get to my second term, I've got 16, and now I'm multiplying it by 1/2, or equivalently dividing by 2. U sub 3, I've got 16, but now I've multiplied by 1/2 twice. I've multiplied by 1/2 to get to 8, and another 1/2 to now get to 4. So I've multiplied by 1/2 twice. My u sub 4 term, well, that's going to be 16, and now I would multiply by 1/2 3 times. So again, I think we can spot a formula here. U sub n, that's going to be 16. I'm multiplying by 1/2, and I'm raising that to the power of n minus 1. Right, so I've got my subscript of 4 and my power that's 1 smaller of 3. I had my subscript of 3, and again, the power was 1 smaller. So that's what we're saying here. If you have the subscript of n, the power should be 1 smaller. Once again, just like before, I mean, this expression, u sub n equals 16 multiplied by 1/2 raised to the power of n minus 1, that could absolutely be simplified and rewritten. So just keep that in mind. A couple other things we should talk about here real quick. This sequence is known as a geometric sequence. Let's talk about that real quick. And a geometric sequence is when you're multiplying by the same number each time to get to the next term in the sequence. Here, our value, we label it as an r, is 1/2. That's what we're multiplying by to get to the next value. And this is known as the common ratio. So we had the common difference. We had the common difference when it's an arithmetic sequence, and we've got the common ratio when it's a geometric sequence. Okay, so let's just find a formula here real quick. We're going to find an expression for the sequence 2/5, 3/8, 4/11, 5/14. Well, notice my first term, I'm just going to write it down, 2/5. Now, what's happening from the first term to the second term? Well, it looks like I'm just adding 1 to get to the next number on top, and it looks like that's the pattern in general. I'm just adding 1 each time. And the denominator, what am I doing? Well, I'm starting with the number 5, and it looks like, well, I'm adding 3 to get to the second term, right? I'm adding 3, adding 3, adding 3 to get to the next terms, the next successive term in the denominator. So it looks like u sub 3, well, I've started at the number 2, and now I've added 2 multiples of 1. And in the denominator, I've added the multiple 3 2 times. So just like before, I think we kind of saw this pattern. If we look at the subscript, the multiples of 1 that we're adding in the numerator is 1 smaller, and the same thing for the number of 3's in the denominator. So in general, it looks like we could write our formula u sub n. We would be adding 1 fewer 1's, so we would have n minus 1 in parentheses. And the same thing, we'll have 5 plus 3 multiplied by n minus 1. As before, this could be multiplied out and simplified, but I'm going to leave it just like that for now. Okay, so another type of sequence here. Let's look at the sequence. We've got 1, 1, 2, 3, 5, 8, 13, 21, 34. You may recognize this sequence. This is the famous Fibonacci sequence. And to get any specific term in the sequence, what are we doing? So let's look at the number 5. Well, what we're doing is we're adding the 2 numbers prior. Likewise, if we look, for example, at 34, I'm adding the 2 numbers prior. So we could label this as u sub 1, u sub 2, u sub 3, u sub 4, u sub 5. Let's look in general. Maybe I call 34 my generic term u sub n. Well, the term before it would be u sub n minus 1, and the 13 would correspond to u sub n minus 2. So to get any generic term, well, let's see, let's come up with our formula. So to get u sub n, what are we doing? We're adding the 2 numbers prior. That would be u sub n minus 2 plus u sub n minus 1. But notice that only works if n is greater than or equal to 3, right? Because it doesn't really make sense for u sub 1 and u sub 2. So n has to be greater than or equal to 3. And we also have that u sub 1 is equal to 1, and u sub 2 is also equal to 1. So this would be a formula. And notice what I'm doing is I'm defining a term, u sub n, in relation to prior terms. And this is what's known as a recursive sequence. So a recursive sequence uses the previous term or terms to find the next term. And so as you just saw, the general notation might look like something like u sub n minus 1. Well, we also had to use u sub n minus 2. So a quick example here. We're going to find the first 5 terms for the recursive formula. U sub n equals 2 multiplied by u sub n minus 1 plus 5, and u sub 1 is equal to 3. So we're going to find the first 5 terms. We've already got u sub 1, so we'll find u sub 2, u sub 3, u sub 4, u sub 5. Okay, we'll find a next one just for good measure. So u sub 2, that's going to be 2 multiplied by u sub 1 plus 5. Well, u sub 1 was given. That's our value, positive 3. So 2 times 3 is 6 plus 5. That's going to give us 11. And again, now we just insert that into the next formula. So u sub 3, that's going to be 2 times u sub 2 plus 5. But we just found u sub 2, that's 11. That's what we're substituting in. So we've got 2 times 11 plus 5. Well, that's 22 plus 5, that's 27. And we'll just keep this up. So now we substituted in 2 times 27 plus 5. Well, let's see, what's 2 times 27? That looks like 54. Plus 5, that's going to give us 109. U sub 5 will be 2 times 109. Again, plus 5. 2 times 109, that's going to be what? 218 plus 5. So we've got 223. And last but not least, we'll have 2 multiplied by u sub 5, which is going to be 223 plus 5. We're having fun. This is 446 plus 5. That's going to give us 451. Okay, so very tedious, but you're just calculating a new value and then inserting that into the formula to sort of update and keep going. So let's look at sigma or summation notation. So again, just an example here at random. So we'll start talking about summation or sigma notation. I usually call it summation notation. And you'll see this big epsilon, it looks like a big E, this Greek letter that looks like an E, capital E. So consider the sum 5 plus 8 plus 11 plus 14 plus 17. Okay, and we're going to stop at 29. So I think you can see the formula here. We've got the formula. It looks like we're adding 3 each time. So if I look at the numbers, right, I'm adding 5 and 8 and 11 and 14, and eventually I'm going up here to 29. So what we're going to do is we're going to try to come up with a notation that we can write this formula 5 plus 8 plus 11, the sum, we'll actually call it a series as well, up to 29 a little more compactly. So the first thing I'm going to do is I'm going to try to come up with a formula for the nth term. So again, here's my u sub 1, my u sub 2, my u sub 3, and I'm going to do this one a little bit faster. So it looks like we start with the number 5, and I'm adding multiples of 3. That's my common difference. But it looks like, at the first term, u sub 1, I'm not adding any multiples of 3. At n sub 2, I'm adding 1 multiple of 3. So I'm always adding 1 fewer than the subscript, multiples of 3. So that's going to be a formula for my u sub n. Now, notice my first term, that's going to correspond to n equals 1. Well, let's see. How many terms do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8. We've got 9 terms. So this would be my n equals 9. What we're going to do is we're going to write this more compactly using summation notation. So my first n value is going to correspond to the number 1. My largest n value that we put on top corresponds to the number 9. And then I just plug in my general formula for a term. So I've got 5 plus 3 times n minus 1. I'm going to put this in a larger set of parentheses. So this number at the bottom, this value of n, this is called the index. And the number 1 that we're starting at, that's known as the lower limit. The number at the top, that tells you where to stop. That's your upper limit. And then the value that we're actually computing, this formula, that's known as that's a formula for it's called the general term. Okay, so we'll expand some out. We'll do some examples here in a second. But the idea is whatever the index is, so we're starting at n equals 1. So let's look at our series here. N equals 1 to 9. We've got 5 plus 3 times n minus 1. Notice if we plug in the value n equals 1, we're going to get the number 5 plus 3 times 1 minus 1, 1 minus 1, which will be 5 plus 0. So I'm just going to erase that. Notice we'll just get 5 as our first value out. And then what we do is for summation notation, so we started at n equals 1, and now we just bump it up. Now we bump it up to n equals 2, and again we compute. So if I look at my formula, I've got 5 plus 3 times, I would have 2 minus 1. Well, that's going to give us 5 plus 3, or notice that's going to give us our next value, which will be 8. If I plug in n equals 3 into my general term, if I plug in n equals 3 and simplify, I'm going to get 5 plus 3 plus 3, which is going to give me 11. So I'm now expanding out the summation notation, and eventually I'll keep going. Eventually I'm going to stop at n equals 9, and when I plug 9 into this formula, well, I'm going to get 5 plus 3 times 8, or 5 plus 24, and again, that's going to give me 29. So that's the idea of how we're writing a formula more compactly using summation notation. So let's see here. A couple examples and then some questions for you all. So calculate the given sums. So in part A here, we have from 1 to 5 of negative 1 raised to the power of n and n squared. So let's just write it out. So for n equals 1, I would have negative 1 raised to the power of 1, and then 1 squared. So that's going to correspond to n equals 1. And then I would plug in next n equals 2. So I would have negative 1 squared, and then I would have 2 squared. Well, let's see, then I would have negative 1 to the third. And again, I'm plugging in now, I'm replacing the n, so I would have 3 squared. Plus negative 1 raised to the fourth, that would have 4 squared. And then I'm going to have plus negative 1 raised to the fifth. And then I would have, let's see, 5 squared. So I'm just substituting n equals 1, n equals 2, n equals 3, n equals 4, n equals 5 into my formula, negative 1 raised to the n times n squared. So if I simplify, notice I would have negative 1, let's see, plus 4, then I would have minus 9, plus 16, minus 25. All right, so what does this give us here? What's the easiest way? I'm just going to be lazy and add them across. There's certainly some formulas for this. So let's see, negative 1 and 4, that's going to be 3, plus, okay, negative 9 plus 16, that's 7, minus 25. That's 10 minus 25, which will leave us with negative 15 as the value of our sum. Let's see, for part B, let's see if we can fit that one in here. So notice, okay, so now we're starting our index at n equals 3. There's nothing that says you have to start at n equals 1. So I'm going to plug 3 into my formula everywhere there's an n. So I would have 3 squared, plus 3. That's going to be my n equals 3 term. Then I would plug in 4. So I would have 4 squared plus 4. Then I would bump it up. I would have 5 squared plus 5. And then lastly, I'm going to stop at 6 squared plus 6. So I've got my n equals 3 term, n equals 4, n equals 5, n equals 6 in my formula. I'm just replacing 3, 4, 5, and 6. And again, now if I evaluate this, we'll see what we get here. So 3 squared is 9 plus 3, that's 12. I'm going to have 16 plus 4, that's 20. I'm going to have 25 plus 5, that's 30. 6 squared is 36 plus 6, that's what, 42. So I've got 50, 62, looks like to me 104. So we're just expanding there and simplifying our summation notation. So now we're going to rewrite. Here I've got a couple of infinite series again, and that's when you're adding up infinitely many terms. I've got 6 plus 9 plus 12 plus 15 plus 8. So again, all I'm really going to do is just try to figure out a formula for the general term. So u sub 1 is going to be 6, u sub 2 will be 9, u sub 3 will be 12. Like, again, what am I doing? I'm adding 3 each time to get to the next term. So I could write 6 as 1 multiple of 3. I could write 12 as, well, I've got 6, and I've added 3 twice. So it looks like my nth term, I could write that as 6 plus 3 times n minus 1. And notice we keep seeing this sort of formula every time for our this would correspond to a geometric sequence, 6, 9, and 12. And we've got this formula where we take the first term and then we subtract away 1 from our term that we're looking at, u sub n. So keep that in mind as we go forward. So our general term, we could write that as 6 plus 3 multiplied by n minus 1. So now I just need to start my summation in the right place. So my summation in this case, well, I guess I would start with n equals 1. That's my first term. And notice there's no stopping value in this case. We just keep going on and on forever. So here we could write, instead of n having an upper limit, like we had 5 and we had 6 in our previous examples, since this does not stop, our summation will go to infinity. Okay, so notice our next sequence, we've got negative 4 plus 8 minus 16 plus 32 minus 64. This is going to be a finite series, so instead of our upper limit of integration going to infinity, we'll have a stopping point. Well, let's see if we can figure out a formula here for our general term. So our first term is negative 4. Now to get to the next one, it doesn't look like we're adding the same number. It looks to me like we're multiplying by negative 2. So if we take negative 4 and multiply by negative 2, we will get positive 8, which is going to be our second term that we're adding up here. U sub 3, well, notice in that case, what are we doing? It looks like we're taking negative 4, we're multiplying by negative 2 to get positive 8, and then we're multiplying by another negative 2 to get negative 16. So we could write this as negative 4 multiplied by negative 2 to the first power. 16, to get negative 16, again, I've taken negative 4, and now I've multiplied it by negative 2 squared. So it looks like to get our nth term, we've got negative 4, and then we're multiplying that by negative 2 raised to the power of n minus 1. Okay, so whatever my subscript is, I've got negative 2 raised to 1 fewer as an exponent, and again, all that's multiplied by negative 4. Once again, you could absolutely simplify this. You could absolutely simplify this, but I'm going to leave it as it is. Okay, so to write this in summation notation, notice we've got 1 term, 2 terms, 3 terms, 4 terms. Our fifth term, u sub 5, would be negative 64. So let's see, we said our general term, that's negative 4 multiplied by negative 2 raised to the power of n minus 1. We're starting at n equals 1, and it looks like, again, our last term would correspond to an n equals 5, and that would be our more compact summation notation. Once again, you could certainly clean this up and rewrite it, so this solution for the summation is not unique. All right, let's look at a few questions for you all to try. So number 1, we've got A and B. We're just going to calculate the sum, so just expand out those series and simplify. Part 2, we've got a little word problem about investing money. Part 3, we're going to take a couple of series and rewrite them using summation notation. And part 4, you've got a recursive sequence, and we're going to just expand a few terms. We're going to find the terms U3, U4, and U5.